there. And if they need that, that's there. So share. All right. So I just need to get this one. Oh, sorry.
Oh, you're good.
All right. So let's just grab a couple examples from where we're at chapter 2. And specifically, I think something that we should at least know that we have down is getting rid of H in a instantaneous velocity problem. We had a couple of those.
Yeah.
If you've done it once, you're probably comfortable-ish with it. But let's look at one here to make sure, because that is our end goal. And then we'll look at some precise definitions of limits.
Okay.
Is that all right with you?
Yeah, that works.
Find. I think this one might be a good. Let me. This here. So we'll look on the interval from 0 to 2, and we'll look at the function. Four square root of x plus 1. So, I'm sorry, 4x plus 1. Is this visible or does it need to be bigger?
No, it's visible.
So we're going to look at, I'm writing at a weird angle. I'll make it all work in a second here.
Okay.
I'm going to move my laptop so my writing, I can see my writing. Oh, that's perfect. Do this without locking up my computer. My computer has this thing, if I bump it in the right way, it freezes. Something loose on the video card, I think. That's better. So, whenever we find an average, we can think about, your book's going to use H as being B minus A. And so in this case, H is going to be 2 minus 0. And we're going to want to look at then what happens to the function. So I'm just going to put the average of f, because we're looking at the average, is f of x plus h minus f of x all over h. So substitute in 2 for h, I guess. And upstairs you're going to get 4 times x plus 2 plus 1 minus 4x plus 1 all over 2. Because that's what we found for h. Making sense?
Yeah, so the h is like the time interval. There could be a time interval.
Since we're just talking about the function in its most general sense, we're going to say h is just the change in x.
Okay.
It is a step size, is technically what it's called.
Oh, okay.
Okay. Checking participants. All right. Oh no. Why? Yeah. Right now we're looking at this step size, or this step interval. So we turn this into a step size, and then we process what happens with it.
Okay.
In our case, I'm going to distribute the 4. And we get this is happening on this interval. Well, we can actually look at this because we do have the 2-point values, right?
Yeah.
So we can make 0 x sub 0, and we can look at this between the 2 points. So the upper bound, right? So we're going to substitute x. We're going to put in the starting point or 0.
Oh.
Right. So we'll look at how it averages from the start to the end. So we'll put in our 0 for here, so we'll get square root of 9. We'll put in our 0 for here, we'll get square root of 1. And on average, that has a slope of 1. All right, so we have some starting point that we come from, which is 0. We go over an interval of 2. We can process the interval through. What we can do is we can look at what happens for a generic interval size. So let's just say we're worried about how h itself processes. So we're going to come over here, so my f of x was 4x plus 1 square rooted. And I'm just going to let h be h. So our function becomes, again, I'll rewrite my difference equation here. And we kind of know that we want to get a limit where h goes to 0. It's going to be one of our games.
Yeah.
Is we want to try to get h go to 0. So I've got to somehow free the h's up here, the h up here, and so that it can interact with the h downstairs. So what I'm going to do is these square roots bug me. And I have square roots separated by a minus sign. So the thing I can use is I can multiply it by the conjugate in the form of the number 1. I'm free to multiply anything by the number 1. So what I'm going to do is I'm going to multiply this by the conjugate of the upstairs. So I'm going to put a plus sign between the two square roots.
Okay.
But to not change the value of my thing, I have to make my denominator look like that. Because now this big chunk of stuff here is the number 1.
Yeah.
So I'm multiplying it by the number 1. What I'm hoping for is this became a difference of squares.
Mhm.
So my answer is going to be the first thing squared minus the second thing squared over this new larger bottom here. Give it a little plus 1 down there, sorry. And what I've done to the top here is if I put this 4 through here, I'm just going to look at the numerator. Okay, well, we know the denominator is going to do what the denominator does.
Mhm.
The parts of the original function, the 4x and the minus 1, cancel, leaving me a 4h upstairs. And then downstairs I have h times 4x plus h plus 1 plus the root of 4x plus 1. And the h's cancel. And so I end up with 4 over what was the original numerator. And now I can actually put 0 into h, because I'm not going to get a division by 0 error.
Mhm.
So I'm going to get 4 upstairs, and I'm going to have 2 times 4x plus 1, or 2 over 4x plus 1. So a lot of the tricks that we'll be doing with this difference equation is to try to get h's to cancel so we can replace them with 0.
Okay.
In the end game, that's looking to get the limit as h approaches to 0 is our goal. Yeah, you're in handwriting hell, aren't you, for my handwriting on the screen thing?
Huh?
Handwriting hell for my screen thing.
Oh yeah. Mine isn't much better.
My tablet, mine goes way worse. Well, at least in this format with it on the screen behind me.
Yeah.
Questions on that? Do you see the format?
Yeah, so like the goal is to just try and get the h out of the equation.
Yeah, and normally it's trying to find a way of pulling out factors of h upstairs so that they can cancel factors of h downstairs. Because we're always going to have an h downstairs the way the equation is set up.
Yeah.
Another one. Let you fight with one here. Brandon, if you need in here, I'm just using this as a spare room.
No, I'm trying
okay.
I'm trying to
Sorry about that. Look at So you're going to use f of x is going to equal x squared plus 1. And I'll even write it in its formal notation. We're going to want to find the limit as h approaches 0 of f of x, which means we'll have the limit as h approaches 0 of f of x plus h minus, whoops. I'm going to put the average thing around that, right? Because this thing we're calling the average.
Yeah.
And so drop in x plus h for each side and x for each side, and see if you can get the terms out. So take this and put it in for x squared,
Mm-hmm.
and figure out what happens here, and then leave that as normal. Just watch your sign on it.
Okay.
Do you get something like that for your upstairs? For the first step, you're gonna drop in x plus h in place of x. So
Okay.
make sure that whole thing gets squared. Okay?
Yeah, that makes sense. I was doing it different.
Yeah, yep. We get middle terms, unfortunately.
Okay.
Did you get something ugly like that? So if I square this, I'm going to get x squared plus 2hx plus h squared. Comes from squaring this, and plus 1 hangs out at the end.
I tried to do the a little bit higher.
Which bit?
I did x, like I
taking it apart, we're putting it together because this is being squared. So we're going to need to we're going to need to do here is we're going to need to expand this out. So when you square this, it
Yeah.
expands out to a larger form.
Okay.
Hey Robert, can you hear me?
Yeah, audio's good on my end.
And audio's good on my end. Good, good. All right.
Great.
We're looking at section 2.1 and 2.2 using the difference equation, and we're doing it around limits.
Understood.
So what you will see in all of these expansions, in general, is notice the x squared, there's a negative x squared.
Yeah.
The x plus 1, there's a negative 1. The parts that make up the original function should end up canceling back out.
Oh.
And so if I look at the cancellations I have here, and Robert, you're seeing the screen all right?
Yeah, everything's good.
Good, okay. So I'm pointing to the screen in the room here while talking about it, so I'm going to colorize it here also. So the parts of the original function, the x squared plus 1, are subtracted out, and what's left behind upstairs is the effect of the change. So, and that's really what the difference engine tries, or the difference equation tries to encapsulate, is by taking the function plus the change minus the function. Really, numerically, what gets left upstairs in the numerator is the effect of the change. But algebraically, what we can see is which terms the change is really affecting. And in our case, we can pull out an h. And Robert, we've been making fun of my handwriting. The tablet I have isn't like an iPad, so I have to kind of look up at the screen while writing on the tablet. So my handwriting goes 50 times worse. So I'm trying to
that's a
slow
pain in
down.
the ass, I got you. Yeah, no worries. I'm following.
Good, good, good. If you have any questions on my scribbles, just ask.
Would you just be able to scroll up?
Oh yeah,
Just because I came in a little bit late on this one.
right there is where we're at from there.
Perfect, thank you.
And really, the end game here is, as we saw, is we want to get the h's to cancel. We specifically want to get the h out of the numerator. It's okay if we have h's upstairs.
Denominator.
Yes, thank you.
Yeah.
Did I say yesterday I think I'm a little dyslexic?
Yeah.
Like things that are invertible. I think when I think quickly, I'm thinking the pair, and I sometimes grab the wrong part of the pair. I was really noticing it with my 3 and my e yesterday. It was really weird. So if now we're able to put the 0 into this, we're able to have this limit go to 0 because I won't have a 0 in the denominator. Because all said and done, the relationship is 2x plus h, and so when h goes to 0, this becomes 2x. And we are actually going to call this thing the derivative on Tuesday. We'll give it a name, and we'll start finding parts that we can do for it. This process will be called the derivative. We'll look at some special limits. Robert, did you get copied what you needed?
Yeah, I'm caught up. I can just do the rest out.
You sure?
Yeah, thank you.
All right, I'm going to look at something that gets useful for doing these. I might have done it in class, but I really always want to. One of the things that we will get when we have this f of x plus h minus f of x is this part that drops in here, this x plus h, can sometimes end up inside of x to the fifth, x to the sixth. That can get really large. And so we want a quick way of calculating what happens when we take something to powers, to the nth power here. When I was in Calc 1, I would write this out. As a string of multiplications. I'd FOIL the first one. Then I would distribute all the variables to the next one. And it telescoped out really large. I think it was in Calc 2. One of the people I was studying with said, why don't you use Pascal's triangle? And I was never taught it. I actually make sure I teach it in college algebra now. Because it's not hard for us to find a function. Let's say, let's look at one. I'll use f of x will equal 3x to the fifth minus 2x squared. And I'll tag a nice little plus 4 on the end because I just want to be silly. It's not hard to find functions like this that we need to do this process for, at least to check it. And it is useful to see how terms collect. So I want to focus on the yellow bit here of just any first term and any second term, how I take it to the nth power. And so if you've seen Pascal's triangle before, just smile. If you haven't, we'll work on putting it in. And if I briefly went over this in class, I just want to make sure we're comfortable with it. And this gets locked on the video because this pops up enough. So Pascal made a triangle. He starts with 1 on the top. And the first row will have 1 element. And the second row will have 2 elements. And the sides will always be a 1. So the second row gets a 1 and a 1. Now, to then make the triangle for the third row, you use 1 plus 1. So you start with your 1 on your sides, because the sides are always 1, and I need a middle. So 1 plus 1 is 2. So I'm adding the 2 things the middle touch, right? You think if I were creating a middle out of here, it touches these 2 sides. For the third row, there's going to be 1s on either side. And I need 2 things in here. And so the first one is 1 plus 2, because the thing's going to touch the 1 and the 2. And then the other ones would have appeared out of this bit here. It touches the 2 and the 1. And so I add the 2 plus 1. And so for each row of Pascal's triangle, so I'll create another element here. The first element's going to have to come out of here. So it's going to add the 1 and the 3. Gives me a 4. The next element's going to fall out of the middle here. It's touching the 3 and the 3. So it gives me a 6. And then the other element here is touching the 1 and the 3. It gives me a 4. And so this was a creation he made. This is part of what's called the binomial series. But it actually does something neat for us. And I'm going to do all of these by hand. And then I'm going to show you how the Pascal we'll use. Because I think, let's see, this is the first, this is the 0th, first, second, third, fourth. Think upstairs here, when I did the thing I was looking at, my power's to the 5th. So we're going to need the 5th row to work with the 5th power here. So I'm going to build the first 4 rows by hand to compare what's going on. And then we're going to create the 5th row and see how it makes this easier. So what Pascal noticed was if I take A plus B, so I have something up front and something up at the rear. To the 0th power, anything to the 0th power is 1. And so that's kind of the top row here. It's the 0th power. To the first power, it's itself, a plus b. And what I have is the coefficient of 1 times a plus the coefficient of 1 times b. So it looks like this second row. These numbers tell us the multiplier that's going in the coefficients. So if I square something, I get the first term squared, and then I get this middle term of 2ab, and I get the last term squared. And the multipliers in front of the things here are 1a squared plus 2a times b plus 1b squared. So this row is telling me what the multipliers or the coefficients are. And if I watch my powers, I was to the second power. Each term has 2 powers. I really secretly underneath the hood, I'm doing a squared b to the 0, but anything to the 0th power is 1. And a to the first, b to the first, and 1b, whoops, sorry, a to the 0th, b squared. So the powers between a and b add up to the number I had, and I start with a being the highest and it works its way down, and b starts with it being the lowest and works its way up. So it zippers on both sides. So that means a cubed, with, if I were to expand out a cubed, well, I'm going to have a plus b squared times a plus b. So I'm going to have a plus 2ab. Oops, get my squaring in here. Right, we already worked out a squared, so I'm going to write that down here. And I'm going to multiply that by a plus b. So if I multiply a through each term, I'm going to get a cubed plus 2a squared b, right? I'm taking a to each term, plus ab squared. So a multiplied by this, a multiplied by this, a multiplied by this. And now I'm going to multiply b by each term. So I'm going to get a squared b plus 2ab squared plus b cubed. And if I gather the like terms, I have an a cubed up front, because there's only one of them. I have 2a squared b and 1a squared b, so that's 3a squared b. And I have an ab squared and 2ab squared, so that's 3ab squared, and a b cubed at the end. And notice those coefficients out front are the next line of Pascal's triangle. Again, a started with the power I was going through. I was looking at a cubed. So a cubed, I start with the power of 3. I work my way down in a's and up in b's. So without expanding, I could look at b to the 4th. I know I'm going to need these coefficients. My answer would be 1 times a to the 4th, because I start with a to the highest power, b to the 0, which is 1. So I'll leave it there. And then I'm going to have this coefficient 4. A is going to drop down to a cubed, and b is going to come up to b to the 1st. So my powers still add to 4, which is what I'm finding. And my next coefficient is 6. And a is going to drop down to a squared, and b is going to go up to b squared. My next coefficient is 4. A is going to drop down to a to the 1st. B is going to go up to b cubed. And we always end up with 1 on the end, and b works its way up to 4th. And so we have a quick way of expanding these, which I did not know when I took Calc 1, and some of the problems we see when we have to expand things to the 5th or 4th powers would take me a half hour to do one problem, where my friends were zipping through it, and it was because using this. So my next line for the 5th I'm going to need a new element that comes out of here. So 1 plus 4 is 5. Going to need a new element that comes out of here. So 4 plus 6 is 10. Going to need a new element that comes out of here. 6 plus 4 is 10. Going to need a new element that comes out of here. 4 plus 1 is 5 and 1. So I'm going to have multipliers of 1, 5, 10, 5, and 1. I think a thing that always helped ground me with Pascal's triangle is even things would get a middle, and it's symmetric across the middle. Odd things, right, it's symmetric across a blank middle. It's just a way of kind of remembering things coming through. But what this helps me with here, so I'm going to go back and we're now going to look at this difference equation here. So I'm going to say that I'm going to use this notation. I'm going to say the difference equation I'm going to represent with a prime. I'm going to say it's the limit. That's a little dark. I'm going to use a brighter color. It's Halloweeny. I'll use orange. So our difference equation is f of x plus h minus f of x all over h, and we want to take the limit as h goes to 0. So upstairs, I need to take my polynomial. I'll zoom back up here. The 3x to the 5th minus 2x squared plus 4. So I'm going to 3x plus h to the 5th, because I'm dropping this into the x value, minus 2x plus h squared plus 4. Minus the original function, 3x to the 5th minus 2x squared plus 4 all over h. And so using Pascal's triangle, we can hopefully expand these out a little bit quicker. And again, the general thing that happens is the terms of the function should be canceling itself out, leaving me only things with h in it. This numerator keeps track of the change. But now we know x to the 5th, instead of having to go x plus h times x plus h times x plus h times x plus h, I'm going to use Pascal's triangle. And my a term, a is equal to ax, and my b is equal to h. So I can expand this, and I'm going to worry about the coefficients in a second, but I know it's going to start with x to the 5th, and then it's going to go to x to the 4th times h. Then it's going to go to x to the 4th times h, x to the 3rd times h squared, x squared times h cubed, because they have to add up to 5, x times h to the 4th, and end with h to the 5th. So that's for this first expansion here. And now I just need to keep track of the coefficients. Now you can write Pascal's triangle off to the side, which I did up here, 1, 5, 10, 10, 5. Or recognize this will be to the 1st, 5th, 1st, 5th. I'm going to rewrite my 10 here. That's going to be 10. Leaving spaces for coefficients. I didn't do the greatest job. But it saved me a lot of multiplication. Pascal's triangle was a quicker multiplication to this x plus h to the 5th power. Does that make sense, Jarek?
Yeah.
Robert, you following me?
I couldn't until I started seeing all the work get done for it, like actually fleshing out with this part of it. Like when it was just the triangle, it was like wizardry.
Yes.
So now I'm starting to get it.
Yeah, the triangle is the pattern we're going to apply. The triangle has no
Yeah.
kind of meaning on its own.
Yeah, I see it now.
Yeah.
I couldn't see it until I actually saw the rest of it done out, and now it's clicking.
Yeah, yeah, and I've never I when I was in your shoes, like I said, never used this, and we would get problems like this, and I would take x plus 5 h times x plus h times x plus h times x plus h times x plus h, and these homework sections just took forever. So I always try to make sure at some point I go over it just a little bit, because it saves some pain, and I actually do think it's useful. But x plus h squared we know is x plus 2hx plus h squared. Right, we're used to squaring things, we get double the middle term.
Right.
And plus 4. And now I'm going to come over here and put my minus sign through everything. Yes, Jarek?
Should that x be squared?
Yes, it should be. So I'll put my minus sign through everything. This is just the numerator. Because this is the thing I want to clean up. Now, I'm not going to worry about collecting like terms right now. What I want to recognize is if I now multiply this 3 through, I'm going to get 3x to the 5th and plus 15x to the 4th h plus 30x cubed h squared plus 30x squared h cubed plus 15x h to the 4th plus 3h to the 5th. Again, my numerator here, I'm just going to keep working on the numerator as I scroll through. Now I'm going to take the negative 2 through everything here. So negative 2x squared minus 4. I'm going to keep I've kept x h order here, so I guess I'll say this is x times h. The order doesn't matter as much, but I'll keep it the same. Minus 2h squared. And my lovely 4 just hangs out there going, hey guys, what about me? It's like middle school dances. Hey guys, what about me? And there are like terms that we might be able to collect, but what I really want to focus on is this did what we were going to ask it to do. Here's my original function. The signs have changed. And in the first part, there's my original function. The things I'm going to underline in blue are just how the change is affecting it. So these are all the things that have h in them because the change was affecting it. So the parts of the function themselves, the positive 3x squared and the negative, or the positive 3x to the 5th and the negative 3x to the 5th cancels out. The negative 2x squared and the positive 2x squared cancels out. And the positive 4 and the negative 4 cancels out. That's always going to happen with these, is the function itself cancels out, leaving behind the change. And now I am going to grapple with like terms. I'm going to grab all my x to the 4th h's. So there's one of them. See if I have any. That's h to the 4th. So that's my only x to the 4th h in there. Now I'm going to grab my x cubed h squareds. That's my only x cubed h squared. X squared h cubes. So x squared h cubes are gone. Oops. Let's see. x times h to the fourth. So, and I'm going to make sure I'm checking these, that all these yellow things checked out bigger. Sorry, just going to, those went away. So x h to the fourths. That's the only xh to the fourth. And I think this is always kind of the sad thing is unless the powers are the same in different parts, you really don't get the exact same thing everywhere. You really hope for a lot of cancelization, but you don't get it like you think you should. And now I have an h to the fifth. So 3h to the fifth. And I've taken care of everything but these last two terms here. This minus 4x h and minus 2h squared. So I'm going to rewrite my fraction that I was dealing with. This was all over h. And the thing we want to note is the original function canceled out, but what does every one of these terms have at least one of? H. So I'm going to pull out an h.
I was gonna say a friend.
It's doing better than me today now. You know, it has a friendly h, yes. And so all the powers of h reduced by 1. And luckily, this is something we don't do a lot of, but it shows us how the change kind of, right? Remember, we're no longer looking at the function, we're looking at how the function changes a little bit. And by pulling out all the h's, well, I can cancel the 1 in the denominator. And so now I can take that limit as h approaches 0 that I've been holding on to, because I'm not going to get a division by 0. And this is the part that always made me cry, especially when I didn't have Pascal's triangle and I was doing this all out by hand, is anything that still has an h left in it is going to be multiplied by 0 and goes away. And I'm left with 15x to the fourth minus 4x. And so we do have how a function will change instantaneously. A lot of our early playing with these is to help us define derivatives and to find derivative rules. I'm not going to lie to you, there is an easier way to do this, and that's our goal to do it. But what we really want to do is kind of ground ourselves, especially for some different function types, not just polynomials, of how this change manifests itself and how we can take care of that change coming about.
I'm laughing because I remember because I've already taken calc, it's just I don't clearly do well enough, and also, yeah.
Yeah, no, it's,
I
so...
do remember that.
Yes, so Jarek said, I don't know if you heard, Robert, he has had a calc before, but it was in high school a while ago, and he not where he wants to be for being an engineer, so he's taking it again. So he knows the derivative rule we do, which turns this into like a one-step problem. And I really, really want to focus on the thing that we are getting here is A, why it's going to work, and B, how change works its way through our functions. Because something to the fifth, the change does really affect it odd. Later in Calc 2, you'll be doing series expansions, and this comes back to you kind of backwards. And at that point, these pieces are important where the change comes through. All right, do you have any questions on any of the homework or anything, Robert? Because that's all I really have for today was some stuff from 2122, trying to, do some things on the side, make sure people had Pascal's triangle and whatnot.
Yeah, I was working on 2-3, and I got kind of, I think I was just burnt out at this point. I couldn't really follow what I was supposed to do for 2.3.7.
2.3.
I've done it before, and I remember this was one of the easier things when I was doing calc the first time around.
Mm-hmm.
But I just don't remember what I'm actually doing here.
Yeah, well, and so the delta epsilon, this was the big part of the conversation in class on Thursday was what the delta epsilon process is for. And because you don't really get anything out of it. I do like in the book where it starts talking about it as tolerances, or like if you made a cylinder, you can think of it as the tolerance, and you try to lower your tolerances. But what all its job was to prove that limits exist and that the limit we stated was the actual limit. When we did a limit of x approaches 2 of x squared minus 4 over x minus 2, we looked at this and we said, hey, this is like x plus 2 times x minus 2 upstairs. And so these things cancel.
Right.
And so it's a line that has a hole in it at 2. And I waved my hands and said, if I come down this way and if I come down this way, I can get closer and closer to this thing. And so the delta epsilon process is a language where we can take some delta or change in the domain and some epsilon or a change in the range. And by using an inequality, we'll say these will never be 0. So we can talk about in our domain, we're coming around our point. This would be the x approaches c. Right? We can talk about, because an absolute value is your distance from something. So what this ends up graphically looking like is if this is c, I come forward some delta in the x direction, and I come backwards some delta. And by calling it a delta that has to be greater than 0, I never get to c, but I can talk about any point near it. That was my hand waving here, right? I did a hand waving, but here I now have that hand waving in an algebra form. I can say I'm arbitrarily close to the c value. And that lets me set up equations that I can test if they're true. Because then I'm free to say, well, I can get closer and closer. As long as the equation has stayed true, then that hand waving I did saying I'm getting closer and closer turns into making sure that equation is true for every value. So that's the purpose of the thing, is to take that hand waving and turn it into a format. One of its side effects is and we will be going over 2-3 again on Tuesday. So I warned everyone it's the thing we need to get down, mainly because it subtly comes up a lot later. This time around, it's kind of the introduction. Just pretend I drew a half-decent parabola. You can pretend for me, right?
Dude, it's better than what I could have done.
So let's say we have some point here. This would be the limit of the function, right? The function's going to be approaching that. We know that for sure. Well, we don't know it for sure. We just need to make it a provable statement. For some reason, there's a hole in here, so we can never get to the point. I think and what I want to be able to, whoops, used my wrong function. What I want to be able to say is that I can make some tolerance. And so if we think of the function as a machine, that you put an x in as your input, and you get the answer to the function as your output, then you can look at the epsilon as a tolerance, how close you are to the true answer. And this is actually where this comes back and gets used a lot. And we'll have some problems that calculate it as if you're looking for how good of an input do I need to put in to make my cylinder this size. So if I draw these back, they end up hitting the function here and here, which means that the x values that'll work, the only x values that will work for these are much narrower. And so we have some, whatever, I'm just going to say that was C down here, so I'm getting a little too many lines. This ends up being the C plus delta, and this is the C minus delta. So they set boundaries, right? If I need to be within this distance to my output, then my input needs to be within this distance.
Yeah.
And we can end up setting the two endpoints equal to each other. We can set this upper endpoint in epsilon has to equal this upper endpoint in delta. So the algebra that we do ends up giving us endpoints, and we set the endpoints equal. And that lets us know how good the delta is. I could turn around and say, okay, I need to be within 0.005 for my answer, and I come down, and the equation I get will tell me delta needs to be in 0.01 or something like that. That equation that we got gives us the relationship between the endpoints. And as long as those equations are valid, then we can make this arbitrarily small. And your book, again, talks about it as like machining a cylinder. It turned out Richard works in a machine shop, so this conversation went kind of nice. Is that you can think about, I need to make something that stays within a millimeter of the tolerances. Well, then my input needs to be within a thousandth of a millimeter, or however that relationship comes across. And so that's what the process is. Now you said you were looking at 2.3.7?
Yep.
And that's in Pearson, not okay, let me pull that up here. I am on another screen pulling it up. I apologize. I'm just not switching this screen sharing here.
No worries.
Oh, I worry about everything, man.
Dual monitoring.
Let's see, 2.3.7. Oh, okay, so it does list it like this. So, given a graph, is it one that has a graph with these? Yep. All right, so Jeff, trying to figure out how to do this. Bum, 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 bum. Oh, okay. All right, I'm gonna change my share here. And sorry, this is what I look like today. I'll change this.
All good.
Where did my share go? There we go. So this is what I'm looking at here. Can you read that one? So this should be similar to what you have.
Yep.
Are you seeing my mouse on the screen?
Yep.
All right. So given the graph, find the largest value of delta such that for all x, f of x minus L less than epsilon, whenever 0 is less than x minus c is less than delta. That sentence is the definition of the precise definition of a limit. So we tend to word all of our things really close to this. And we have a linear relationship here. So we see our c is going up to 3. And our epsilon around 7 is 8.4. So what it's doing is it's taking 7 plus 1.4, that's this upper bound, and 7 minus 1.4, that's the lower bound. And then when you come back to the deltas, what you get here is this 3.35 is C plus delta. and this 2.65 is C minus delta. So I'm going to switch screens here. Jarrett, can you write down the 2.65, 3, and 3.35?
Yeah.
So what I'm doing is I'm just writing down, this is my C minus delta, this is my C, and this is my C plus delta. So that relates back to how these limits come on the graph. I want to switch over here because I just need to show this as an equation. This is my least favorite thing about Zoom is I have not found a quick swap screen sharing thing. Unless you share your whole computer, and then everyone accidentally reads your email because your email pops up and you check it really quick and you forgot you left it there. So the end caps end up being that I have C and then I have C plus delta.
Real quick,
Yeah.
I'm going to stop you. I just didn't understand the phrasing of the question, and the explanation that you've given already made it so easy.
That's okay. Good. Well, no, I'm gonna, and so you now just subtract C from each of those, and you'll get your deltas on it.
Right.
Right. There will be some cases where you'll get two answers for delta. It happens a lot with squares and square roots, where one answer will be, what did we get? We got 2 minus 4 plus epsilon, and 2 plus 4 minus epsilon, I think, were the two answers. And you'll get this notation where you'll take the minimum of it. Because for some regions, for some epsilons, one of these will be bigger. And as you get closer, it flips to which one is the bigger. And so it tells you to always take the smaller of the two. You'll see that notation you'll see that in the notation of the book. And so you just kind of have to keep track of both endpoints. And as you work your way through epsilon, one will be bigger, one will be smaller. That notation gets some people sometimes. Well, we're gonna.
And I'm sure it'll get me at least once this semester.
And it still gets me because what we're doing is we're figuring out how to deal with infinity. The secret to you guys, there is no quiz on Monday or Tuesday. We're going to do about 2 or 3 of these together in class.
Sure, cool.
All right. That's all I have. You okay?
Yeah, I'm good.
You got what you needed, Robert?
Yeah, appreciate your time.
Hey, that's what we're here for. I'm here every Friday. Sorry I was a little late signing in, so I don't know if you came in earlier. I was finding a room.
Dude, I showed up late. I am glad that you offer this to make up for missed classes, because yesterday I was not feeling alive. So.
Well, and I was about to say you sound a little tired, so rest up, and I hope to see you well on Tuesday, okay?
Appreciate you. Have a good one, guys.
You do the same. Take care.
I wish I was taught that triangle the first time.
I was in the same.
That's like half of the issue. It's like,
The time it takes, yeah.
now I gotta multiply these, and then I'd multiply like one of them wrong. It would set the whole thing wrong, and I'd be like, I don't know where I'm going.
Well, now you see why I do what I do.
Yeah.